I'm still trying to silent. And I should probably start this by describing what metaheuristics are and what the point is. And the point is they're to do with operations research, the optimizing of very large, hard problems. Usually problems like this, discrete combinatorial NP-complete problems, where large problem sizes mean that you cannot completely solve them using things like branch and bound or Nick's various search strategies for his little game. But we do want to find as good a solution as possible as quickly as you can, or within whatever time limit we have available. And metaheuristic researchers and operations researchers use metaheuristics like iterative improver, taboo search, and genetic algorithms, among others, to try to do this. But they have a lot of parameters which must be set. There's a lot of tuning which you have to do. A simple example would be the population genetic algorithm. Use a tiny population and you can guarantee it's not going to work at all. But some of these parameters are actually functional in nature. For example, a metaheuristic describes a very high-level description of how it's going to try to explore a problem. But if you then simply give it a specific combinatorial problem, it doesn't know what to do. You have to give it some sort of interaction operation which it can make use of. And almost all of them make use of one of these three. In fact, they're the only three which I've seen. Perturbation operations, I'll come back to these in a little bit more detail shortly. And what this talk is going to be about is, do they exhibit patterns, and are there functions for managing it and making it nice and easy to build these things? Now, my PhD has been about trying to build a library for building... Oh, I forgot about this. Whenever I'm going to be talking about examples in this talk, I'll be using the traveling salesperson. I'm sure you're all very familiar with it, but a brief reminder, just in case. We give you a fully connected graph where every single edge has a weight. Please find the shortest Hamiltonian cycle. And I've managed to put in some examples of perturbation and neighborhood here. So in this was the greedily generated solution. And this is a perturbation where just the ordering of the cities has been swapped. I have also noticed that most of my examples actually make things worse, almost universally throughout this talk. This does happen in reality, but... and this is a neighborhood where every single possible pair of cities has been exchanged. And most of these will probably make it worse. So, over the course of the last 3 years, I've been trying to build a library of combinators for building and hybridizing metaheuristics in general. And before I can go any further, I'm afraid I think I have to describe the library that I've built. Although most of this has already been done so far at IFL, because it's basically all this stream stuff, the parallel processing that you've all seen. So I'm very interested in talking to the people doing that. My solution ends up being broadly this, that I encode a metaheuristic as a generator for solutions represented as a stream or a list. And then I tug on it, so it becomes a matter of how you build combinators for constructing one of these generators. And so the library ends up having streams, which are actually just lists, but I'm going to be using the word stream throughout this talk to make it easy to read. Lists which are finite, but are actually still just lists. And the idea of stream transformations, which, as you've already seen, can be composed a lot to build nice, complicated pipelines. So to try to explain how this works, one of the simplest metaheuristics is the iterative improver. You have a solution, you generate a neighborhood of new solutions from this, you take one of these neighbors which improves, in the case of our first round, the first neighbor which is generated which improves upon the seed. And you can describe it like this. So this is a function which takes a stream transformation for neighborhoods and a seed. It describes one stream, which is the seed, followed by something, and returns it. The second stream is the neighborhood transformation of the stream of solutions. So it's the stream of neighborhoods. Then we create a stream of improving neighborhoods. And then finally we just take the first element which gets spat out at each point. This is obviously not particularly pretty. So one operation which I've got is this, which takes a neighborhood transformation and creates an improving neighborhood transformation. I'm not going to be showing the code for this. But this allows you to compress it all like that. And then this usage of the seed can also be encoded as a looping operation, which has been seen in the various parallel processing talks so far. And that allows you to turn the iterative improvement metaheuristic into this. But this idea of the map head improvement NF can be removed and composed with other metaheuristics, and that's the advantage of going about it in this way. So to come back to the low-level operations, which is the point of this talk, neighborhoods are a transformation from a stream of solutions to a stream of collections. Perturbations are a stream of solutions to a different stream of solutions. And recombinations, for genetic algorithms and so on, are a stream of collections which will somehow or other create a new solution. And when I started my PhD, I kept on arguing that these were problem-specific functions which simply had to be created by the user for whatever problem they're dealing with. And this is often the way metaheuristic designers seem to treat them. But it's not actually the way I'm now treating them. So the first operation is quite easy. If you have a neighborhood, can you turn a neighborhood into a perturbation operation? And the answer is yes. You simply need to select an element from that, which can be done through the composition with a selection operation, of which these are some examples. So rather like the iterative improver, if you have a neighborhood function, you can compose it with taking the first one, or taking the lowest one, or the maximum one, or a random one. And this gives you a nice collection of different perturbation operations if you happen to have a neighborhood. Going the other way is slightly harder. If you have a perturbation operation and you want a neighborhood, you need to apply that perturbation many times to each element of an underlying stream, which can be done like this. And I have some pretty pictures here, I think. Good. So the stretching operation takes each solution and produces a new stream where that solution is produced, or that value is produced, many, many times. And going the other way simply gathers them up again. You have to be a bit careful in the way that you compose these operations, but in the case of do many, it's always symmetric, so it always works. And it has a strong resemblance to replicate M in the monad libraries, I believe. So in this way, do many allows you to take any perturbation function and get back a neighborhood function. So at this point, I'm going to stop talking about neighborhoods and exclusively talk about perturbation operations. Some metaheuristics make use of this idea directly, this idea of damaging the solution and then repairing it again. But I think it actually is useful more generally for building perturbation operations. In the case of the TSP, a simple idea of damage and repair, you have a complete solution, which obviously is a perfect solution. You damage it in some way, and then you produce a horrible solution. Ideally, you do this the other way around, but anyway. As I said, my examples are all terrible. But that's the basic idea. You're going to, in some way, you're going to destroy edges, and in some way, you're going to put them back. Now, when swapping cities in my previous examples, effectively, the way you repair the solution is determined by the way you damage it. So that's actually quite limited. So I started playing around with the idea of how else can you damage, how else can you repair? And this is a list of different things which I've tried, many of which can be abstracted over problems, although I have to say I haven't actually done that yet. I can abstract with ants instead. But in principle, these I think should be able to be looked at. So you could select randomly, or if you have a heuristic, longest edge, you could destroy the longest edges first, or you could sort them and use some other distribution. And there is also a question of how many edges you should delete to each one, so there's a lot of options. And the one which I've missed is you could use a cycling pattern. If you had a specific pattern of edges you wanted to delete, you could simply cycle it and keep on doing that again and again. Don't ask me quite why you want to do that, but you could do it. Well, it does actually happen in some metaheuristics that the neighborhood operations are effectively a static cycle, but anyway. The repair operations are basically the same, except you could use exhaustive search to actually repair it. So you only have a small amount of damage done, so you can actually put it back together in the right way. Briefly definition of the word right. build these for a particular problem, you end up with a little pick and mix toolbox, and you can build a lot of different variations simply by composing together bits and pieces. Well, do you want me to explain this particularly, or shall I? Okay. So the top one, yeah, sorry, this looks a bit like data generics, but it's actually just me being sketchy about my algorithms, sorry. The idea is that if I have a particular problem and I have a way to do uniform damage, I will destroy 5 things in my problem, in this case the TSV. We will delete 5 edges. And we will then use a greedy strategy to repair the solution. In the second one, we simply do that 15 times. And in this way, we will generate 15 different possible solutions where we've deleted different sets of edges and put them back together greedily. In the last one, again, this is one of those ones which I'm not really sure why you do this, but you could. You could damage it once in one way and then put it back together in a lot of different ways to generate a different kind of neighborhood. So I'm hoping that you believe me when I say that this gives you a lot of options which you can explore, or ideally you can get the computer to explore. Recombination I haven't done anywhere near as much work on, but this is the idea which I've been developing from the ant colony optimization stuff which I've been looking at. The idea is obviously we're trying to generate new solutions from old solutions. But the question becomes, how do you do this? I mean, if I give you a new problem, like a timetabling problem, how are you going to build a recombination system which works and produces valid solutions? In the case of the TSP, let's say you wanted to recombine these two. A naive approach is to approach this a bit like just taking 2 strings and slicing them at some point and putting them back together. So we'll slice the first one, and then we'll take the second half of the second one, and that's an linear solution because it will loop on 9. The bar, by the way, is because my latex is not working properly. So alternatively, we'll filter the second solution for any element which occurs in the first half, put them all to one side, and we'll build it that way. But I find that this doesn't really tell you anything about recombination algorithms in general. It doesn't tell you how to build a good one. The best one for the traveling salesperson does common edge detection. It takes a number of solutions, 2, and finds which edges they both have. It then adds some more edges based upon which ones are present in at least one parent, and then it finalizes them using greedy repair. And it's that point which comes up with my idea for how you would go about building recombination strategies in general. The repair strategies can all be reused from the perturbation operations. So the question becomes, how to build these analysis operations instead. So, over the course of this fairly short talk, I think, you've seen the relationships between perturbation and neighborhood, which of course are all known, but you've seen them all captured as combinators. I've then broken down perturbation into this 2-phase process and described a whole collection of different operations, which I've never seen such a list in the literature on metaheuristics which I've read. If anyone knows of such a list, please tell me. And then I've tried to start doing the same thing for recombination. And I think that when trying to approach a new problem, this is actually an easier way to build operations for dealing with it. That if you're starting a new optimization problem and you're simply confronted with the idea of build a neighborhood function, how? But if you're confronted with the idea of build a way to delete things from a solution and figure out ways of putting it back together, now put these things together to build perturbation. Now do that many times. You now have a way to build these things quite quickly. And for my future work, I hope to continue trying to build better ways of combining damage strategies and repair strategies and analysis strategies. How much time do I have?
Well, let's see, 10 minutes.
Oh, okay. Well, in that case, let's skip over that bit, and instead, I'll try selling this. So, Leeds University has a number of people who are very interested in operations research, and one of these, I've forgotten what role he has at the company, but he works professionally in the field. And he was using one of these problems from his work as an example problem for students. Specifically, it was a train rostering problem if you have a train network, how do you put the drivers on the trains in the right places at the right times in order that everyone gets back home and so on. And he was representing as a set covering problem. And he had a particular metaheuristic that he was playing around with, which was basically an iterated damage repair perturbation, using some specific heuristics inside, which were fairly detailed. And when I started building all this, I began to wonder, how should you actually be doing this? This is actually the traveling salesperson again, or specific traveling salesperson problem, rather than that. But it began to exhibit certain patterns. Some of these patterns are very well known. In answer to, not in answer to, but I mentioned earlier the idea that get the computer to do it. Yes, this is just Haskell being told to cross-compose two lists, and I left it for the weekend. Well, I had it repeatedly doing all the tests, so this is actually averages of results rather than single results. So, certain obvious patterns. Randomness is basically bad, at least when used excessively. As is heavy determinism. So this is delete the most likely edge and then put back the whole thing in an exhaust. Yes?
These numbers are scores?
Yes.
Okay.
And lower is better.
Okay.
The geometric pattern is named, it's a curved distribution which is being derived from a geometric progression. I do have the exact numbers somewhere, but it's being scaled to the number of cities in the problem. And it's remarkably stable. Now, my best approximation for the strategy which he was using in his metaheuristic is a geometric most likely strategy. But the best strategy which I found was this one. This is a biased uniform, so it has a 5% chance of taking the most likely solution and subsequently just takes a random solution from the other options. I did try other strategies which I'm not showing you here, for example, the biased uniform with a higher probability, which did not work as well, hence why not here. But this one is universally the most useful strategy. So once I had this, I decided to try it on the set covering problem. I used the open source mixed integer linear programming toolkit, I think that's what it's called, as my exhaustive solver for the problem. So I had a solution, I deleted some elements from my set covering, and I used that to repair it. And it outperformed his metaheuristic. It outperformed its own linear program, or its own integer linear solver it was using over runtime periods of between 15 minutes and 2 hours. It did not beat an industrial solver, unfortunately. But I was reasonably happy with that. So that's the selling point of this. That this rapid experimentation allowed me to identify an idea which I then was able to move back across to another system and gave it a try. Of course, with metaheuristics, there is no silver bullet. There is no one answer which is the right way of doing it. So this kind of experimentation is very necessary. And by moving directly across to a different problem, I might well have found that it was a terrible answer. I got lucky, so I get to say that. At that point, I am going to say thank you very much, and would anyone like to question me?
So, questions?
So also nice this sort of combinator language for describing the operations on as something. Is there a similar sort of language for describing the fixed functions? Because they are also quite difficult to get at the fixed function to work.
Short answer, no.
No.
Not yet. But I'll add it to my to-do list. But no, I haven't tried to.
Common patterns or anything like that? Or?
Lots of summations and counting of things. But I've only really played around with, well, I say only, I played around with some machine shop scheduling and some timetabling which is very difficult without a constraint language, which I don't have, at least not one which I can fit into my system yet. And traveling salesperson, so the full range of things I think is still quite limited. I'll keep my eyes open in case I find a pattern for the fitness functions.
So one of the things you might want to look at is Fritz Hengheim's work, the little language approach that he showed us in his talk yesterday allows you to build a combinator language for fitness functions and then to reflect on it and to optimize with respect to functions and so on. So I believe he's written something about that, but I can't remember where off the top of my head.
Okay, thank you. I wish I hadn't met Adam.
Well,
did you play around with random generation of meta-heuristics? Now that you have combinators.
The problem which I have with that is that if you put the combinators together in a bad order, so to loop a solution system properly, it has to produce as many solutions as it's generating, which means you have to be a little bit careful about this. So I did start to try to write a sort of meta language which said this produces this many and requires this many and has this type, and therefore these things can be plugged together in this order. I just haven't finished it yet. But in the event that you had that, yes, I would then be saying, right, now we have hyperheuristics for Haskell where you simply let it go and get on with it. So yes, it's on my eternal list of things to do.
Okay, any more questions? Okay, then let's thank